So thank you, Professor Papalardi, and thank everybody for being here, at least virtually here. This talk, which is intended to be my PhD discussion, my PhD defense, will be about elliptic loops, and it is a work which is, of course, co-authored by my supervisor, Professor Massimiliano Sala. So in this work, well, in this presentation, I will first give you some background and motivation. Probably the majority of you know about elliptic curves, but I think it's always better to recall what we are talking about. Then I will switch to these curves when the defining base field is not a field anymore, but it's a ring, a very special ring, which is zeta modulo n zeta. And then we extend even more this idea with the main object of our work, which are elliptic loops. We'll discuss their algebraic structure, and then we'll sketch some future research lines. So let me begin with elliptic curves. So what is an elliptic curve? Well, usually you define elliptic curve to be a smooth plane projected cubic over a field K. In this presentation, K will always be a finite field. But in algorithmic practice, when you deal with finite fields, and especially for cryptographic applications, it is much more convenient to define these objects as the zero set of a special cubic equation, which is this one. This will be this term minus this one will be called the Weierstrass polynomial, which defines the curve. And you may define them by picking an A and B, whatever they are, provided that they satisfy this condition here. So there's a closed set of A and B that you may not choose for having smooth curves. So these are two examples. The left-hand side is an example of an elliptic curve defined over R, and the second one is the same curve but defined over finite fields. So I will use these kind of pictures because they are much more nice. But the thing you have to keep in mind is that we are working over finite fields, so the pictures will be much more like this one. So just a set of points, usually a very large set of points. Why are these curves so special? Where we know that these are not just the zero set of a polynomial, but they are also an abelian variety. You may define a sum over these curves. To sum 2 points P1 and P2, you just draw the straight line through these points. You find the third point on the curve, you reflect it, and then you find the P1 plus P2. And in a similar fashion, you may evaluate the double of a point. And there are some few cases to be discussed when the point is this one. I mean, there are some special points we have to deal with, but it is possible to do it, and we may define a sum operation, which works also over finite fields. So over finite fields, you just have points, as I said before. But if you do a toric identification of your domain, you see that the procedure is almost the same as before. To find the P1 plus P2, you just draw the line. Here you have toric identification, so you continue on this side, and then you reflect the point, and this one is the sum. So the very same idea works even over set of points, let's say. So these are the formula you study in usual textbooks. Well, this is the projective formula. You usually see the affine one, but this formula has some problems. There are some issues that strongly demands to be addressed. Well, the first one is that this is not an open definition. For example, if you want to double a point, you may use this formula when P is equal to P is equal to Q. And this is a closed set in the Zariski topology. So as you know, in geometry, you always would like to have formulas defined on an open set. So the first question is it possible to give some open sets in which you may define in which you may define a formula, and of course you want the sum formula to be the same when these sets overlap. The second thing, the second detail you observe is that this has b degree 4. So this means that if you count the degree of the letters with index 1, you get 4. So this counts 1. So you have 1, 2, 3, and this is 4. So this has b degree 4, but is it the best thing you can do? And the last question is kind of mathematical question. May you enlarge this definition to any abelian variety? So may you find an open definition of these sums? Well, all these questions have been answered. So I put here some references. The answer are yes. You may have an open definition, which is the one we use in today's presentation. The b degree of an open addition law is not 4, but it is 2, for elliptic curves at least, and it is some more complicated, but you may define it over some abelian varieties under certain weak conditions. So this is the formula we will use today. Of course, I don't want you to remember anything of this mess, but I just want to point you out that this has b degree 2 if you count the occurrences of variables with index 1. You see that there are in each term you see two variables of index 1 and 2 variables of index 2. So this is an addition formula which works for every couple of points, every pair of points, except those which has 0 y coordinate. So this is clearly the complementary of a closed, so it's an open set, there's a discrete topology, and you may find two other formulas. Actually, one suffices, the one corresponding to the point 0, 0, 1, to have a complete open set of addition law. Okay, so I just portrayed this formula here because this is the one we really use in the future. So let me give you a last piece of motivation. Why are elliptic curves so important, especially for cryptography in the everyday practice? Well, as many of you know, these objects are widely used for creating cryptographic protocols. In the suite B cryptography of NSA, you see that there were because it was changed, but there were 4 main algorithms, and 2 of them relies on the elliptic curve. This one is the Diffie-Hellman elliptic curve, and this is the digital signature algorithm. Actually, I should mention that it has been replaced 2 years ago, but still these algorithms are present in this suite. I can't ensure that they will be in the future, but this is another talk. So why the study of elliptic curves from a mathematical point of view is so important? Well, because if you create a cryptographic protocol and you choose somehow the wrong curve, this may lead you to very weak protocols, and this is something that you strongly want to avoid. And the most famous example of weak curves in this sense are the curves which have trace 1, that are usually called anomalous curves, and there are the curves defined over the finite field with p elements and with exactly p points. So for this special kind of curves, we have some attacks to the problem of the discrete logarithm. This attack is due to Sato, Araki, and Smart, and it consists of lifting the starting point of a curve to QP, so the field of p-adic numbers. Then you multiply by p the result you found. You apply the formal logarithm, which is a map which is kindly well-defined, even completely well-defined in Silverman and many other references. And then you mod out the result, and you end in this ring here. So Sato Araki proved in the work that this morphism is almost always the non-zero map, the non-zero morphism of groups, and with probability 1/p, it is the zero map. So when it is not the zero map, you may immediately break the discrete logarithm because you have a group morphism from the points of the curve to this ring here. So you just move the problem to the ring and then you quotient out and you find the discrete logarithm. So the first question we tried to address and we addressed in this work is the following: is the field of periodic numbers really needed in all this speech? Well, let me say a disclaimer. I also I love periodic numbers. They are so beautiful and so useful in number theory. But in this very special setting, you see the starting point and the final point, which are the one you are interested in for breaking the discrete logarithm, do not involve any periodic expansion. So the idea was that it may be possible to skip all these steps in between and going directly from here to here and find the discrete logarithm for this curve. So this is the first thing we do in our work. To do that, we need to define elliptic curves over this general ring here. They may be defined even over more general rings. In the thesis, we're given a detailed description of this fact following the main reference, which is the work of Lenstra. But in this presentation, I will always assume this to be the ring of our interest. So the first problem comes with the projective space. You are used to define projective space over fields where everything is easy. I mean, you just take elements of the field and you don't want them to be all zero. But if you define them over a ring, then well, first you define them up to multiplication by invertible elements. But second, this is a technical detail, but which is of great importance for our future work. You want the entries to be primitive. So primitivity in the case of this ring here means that not all the entries are divisible by a prime factor, which also divides the modulo. So I've put here two examples. This point here is a legit point, is a legit projective point, because you see both 2 and 3 are not coprime to 6, but 2, 3, and 6 together as greater common divisor 1. Instead, this point here is not legit. These are the points we do not want in our projective space. And that's because 3 divides all the entries of this point and divides also the modulo. So from now on, we always deal with this point here, the first type. We throw away these points. Okay, so following the work of Lenstra, we have defined elliptic curves over a ring. How do you do it? Well, you properly construct the projective space, and you take the zero of the same Weierstrass equation, but modulo n instead of modulo p. So it seems everything seems easy, but it is not. In fact, the fact that the same addition law, or a slight variation actually of the field addition law, endows these curves with a group structure. This is a highly non-trivial result, but it is true. And it was proved in this work here of 1986. What it is not that surprising is that if you define an elliptic curve over this ring, then you have a canonical projection to the standard elliptic curve over the field. This is quite an exercise. So, okay, let us assume that everything is defined properly. It is not easy, but it may be done. So now we are interested in studying the structure of this curve here over this ring, over this quotient ring. So the first result, which is again an easy exercise, is a trivial application of the Chinese remainder theorem. It shows that if you want to study a composite modules, then you just study all the pieces, all the factors of your modulo here, and then you have a direct sum of the roots. So this says that this tells us that it is sufficient to study only the prime factor dividing a number. So from now on, our problem will be to study the structure not of elliptic curve over nz, but over p to the z, where p to the e divides n. And of these curves, thanks to the answer lemma, this is another nice exercise. You prove that this projection, the one we mentioned before, you just take every entry modulo P, is surjective, and its fiber is constant, and the constant size of the fiber is P to the E minus 1. So the corollary of these two results is this nice formula for counting elements of elliptic curves over Z modulo NZ. But this does not answer the question about their group structure. I mean, we know their size, but we do not know the group structure. Why are we so interested in this group structure? Well, because we will use the knowledge of the structure. We first characterize the structure, and then we use the knowledge to determine, to mount another isomorphism attack to the discrete logarithm over these special anomalous curves. So the main ingredient of our receipt is the study of points at infinity. So a point is said to be at infinity if it lies over the infinity point of the underlying curve. So you see, this is the large curve over the ring. This is the same curve over the field, the projected field. And these are the points we call at infinity, because are the points that if you take their entries modulo P, then you get 0, 1, 0, which is the 0 point of the underlying curve. Okay, why are them so interesting? Why are them more interesting than the others, let's say? Because for them, there is an easy way to parameterize their coordinates. This is a proposition that emulates the idea of Silverman of expansion around 0, but it is not the same because Silverman was working over the p-adix numbers, so it has to prove that the series converges by using the completeness of its field. But here we do not have any field, and we have a ring which is not complete. So the fact is that here we don't need to define a proper series. We define just a polynomial. So we do not have any convergence problem. There's in the proof we give an explicit way to construct such a polynomial. And then the final outcome is that points at infinity may all be parameterized in this way. So you take an x, which is divisible by p, the y coordinate is 1, and the z coordinate is this polynomial f applied to the x coordinate. By using this knowledge of the points at infinity, we have proven this first theorem, which states that this is a short exact sequence of groups. So here you have the group generated by this point here, P1, and this is the polynomial I just mentioned before. You take the group generated by this point, you embed it with the identity morphism in the elliptic curve over the ring, and then you project it over the elliptic curve over the field. And this sequence is a short exact sequence of groups. So why is this theorem so useful for us? Well, because as you know, when we have short exact sequences, we have the splitting lemma we may use to study the structure of the middle term here. But we may do it only if we are able to construct a lift, so a section, so a morphism from here to here, which gives the identity when composed with the identity here. And we are able to do it every time we are able to construct such a section explicitly every time the size of the projected curve is not p. So every time you lie over a curve which is not anomalous, then we construct an explicit section, sorry, and then the splitting lemma tells us that this middle term here is given by the direct product of these two groups here. So since this is a coprime order with P, it proves that these objects are almost always cyclic. It is also possible to give a concrete characterization in the for small exponents. When the exponent is smaller or equal than 5, then we have concrete isomorphism defined in this way. I don't want to lose much time on this. I will show you an example of, about how this on how this works. So we want here we have the points of the curve over this ring here, zeta and modulo of 49 zeta, and we want to sum the red point and the blue point. So given our isomorphism, we just take the projection here, we evaluate the second entry here, which is just a number, and then we sum the two entries here. So to sum these 2 points, we just sum 2 and 3, and we find 5. And then we sum 2 points over the underlying curve, and we find this point here. So this is the result of the sum. So this shows that what we have given is a real concrete isomorphism between the objects, the considered objects. But one case is still missing. What about when we do not have a section here? So we are sure that we have it when the order of this curve is p, but is not p, sorry. But when this curve is anomalous, what can be said? Well, in principle, we have 2 possibilities, because this is a subgroup of this object here. So we have a subgroup of this size. So it may be either a cyclic again, or it may be split. And as a matter of fact, both of the cases may occur. So the cyclic case is the most common. Almost always you have a cyclic structure even for the anomalous case, while the split case occurs with probability 1/p. So this concludes the study of every possible group structure arising as a point group of an elliptic curve. And since this characterization is complete, we also used this information to create a proper isomorphism attack when we are in the cyclic case, so the most common case. When you use primes of cryptographic size, this is almost always the case. So this is a proposition which gives an explicit isomorphism. Well, this is not an isomorphism, it is just a morphism which a given kernel that we know from the curve to the base field. And then a corollary is that if we take any fiber of the point and we apply this morphism theta, then we have a real group isomorphism. And this means that you immediately break the discrete logarithm in this setting. So I provided you with an example. Usually I like small examples, but this time I try to mount an example which has some cryptographic relevance. So in this work, Monera and others proved that there's an efficient way for generating large anomalous curves. So I've taken the curve they proposed, which is based on a field fp with p of 160 bits, and I try to I've taken 2 points, the one with x1 and the one with x3, and if epsilon you have 2 choices, but you just choose the smallest one. And I try to break the discrete logarithm on these points. They claim that it may be done in a few seconds, but with Magma, I've done it in 0 seconds a few days ago by using this idea I just told you. So there are 3 steps. First, you compute the lift, and this is very easy. You just solve a linear equation in this ring here, so it takes 0 time. Then you compute the multiple of these 2 lifts. So you compute this theta function, and you find 2 very large numbers. And then you just take the quotient of these 2 numbers inside the starting field, and this is the discrete logarithm. So it really takes 0 times to be performed in Magma. Okay, so I'm halfway in the presentation, and I never speak about elliptic loops. So where elliptic loops comes into play? Well, if you look at this attack, here you have some arbitrariness in the choice of A and B, namely that if you shift B by a multiple of P, again what you find is a curve which still projects on the same curve with another operation. So the point is that may we deal with all these lifts somehow together. So this is a picture of an elliptic curve over this is the projective plane, and this is the curve, and this is the idea we have when the underlying field, the underlying ring is a field. But what happens when we embed all these idea in a ring? So over the ring, the curves are much thicker. You have another dimension somehow. Here in the vertical line, you have the projection. So all the points above the same point, and those projected to the same point in the underlying curve. So this is the picture one may think of at the beginning, but instead what is really happening is that this curve intersects in a diagonal way the large projective space. So how do we study all at once all these possible strange diagonal curves in this large projective space? Well, the easiest idea is just to consider all the points which are projected over the curve in this space. And this is what we call an elliptic set. So the elliptic set, it is formally a solution, still a solution of an equation, but a strange equation because we have this non-zero divisor, this zero divisor multiplying the Weierstrass equation. And this means just that we do not require the Weierstrass equation to give 0, but we require it to give just a number which is divisible by p. And if you think of it, it's kind of a natural way of generalizing the thing, because when you are over a field, you want the Weierstrass polynomial to give you 0, which is, in other terms, you may state it as the evaluation of the Weierstrass polynomials is contained in the maximal ideal of the field, which is 0. But in this case, here we have a more general ring. So what we are asking here is this value to be contained in the maximal ideal of this larger ring. So it is somehow, I mean, I feel it's kind of a natural way to generalize the previous topic. But here the details matter a lot. It becomes much more difficult to define an operation on this set. And we have done by taking this operation, the one I've shown you before at the beginning of this presentation. But this operation is not defined when you have may not be defined when you have even order points. So we assume our elliptic loops not to have these kind of points. It is not a reasonable assumption, as you know, for cryptography you usually consider prime fields. So for us, I mean prime curves. So for us, we just require the curve to have odd order, which is much weaker. So 55 points is fine for us. Okay, we have called it loops, and there's a reason. It is because it is an algebraic loop. Namely, this operation with the elliptic sets is closed and commutative. It satisfies the Latin square property, so this kind of linear equation may always be uniquely solved. And there's the identity element, which is the same identity of the curve. So with this fact, I have bothered my colleagues so much. You would hope it to be a group again, but in fact it is not. And that's something that for a mathematician is really sad, having a non-associativity operation, a non-associative operation, because you mean everything you know, everything you use in your everyday research relies on associativity, more or less. But these loops are not associative. So this is an example of 3 points that do not associate. So the first question is, how rare is this non-associativity? Is kind of a detail or something that may be overcome easily? Well, the answer is no. We have a complete characterization of the elliptic groups. So these are the list. So these 6 loops are the only 6 loops which are also groups. So all the others are not groups. So the operation is almost always non-associative. And this is the list of groups arising from these guys here. I grab the occasion to thank Professor Semer for having pointed us out that these 2 structures were wrong in the first version of the thesis. Now they are corrected. Okay. Okay, now we know that we do not have associativity. What could we hope for? Well, at least we could hope for having power associativity, which is a weaker version of associativity, but it is something that we strongly would like to have. And it means that when you compute a multiple of a point, n plus n times this point, you may compute it in many ways. You may do, for example, p plus p plus p plus p plus p and n plus n times. Or you may compute, for example, n times p, so p plus p plus p n times p, so p plus p plus p n times, and then add them together. So if you have associativity, of course, these quantities are equal. But if you do not have, then in principle, and it often happens that for non-associative loops, that these may be different. So is it true? Are they different or not? Well, to make a very, very, very long story short, it is true that you may always do this operation. So every elliptic loop is power associative. But this theorem, I've called it theorem, but in our thesis, it's just a corollary of a much nicer theorem. This is much more nice, in my opinion, but it's even much more complicated to be stated. And this theorem provides you with sufficient condition for 3 points for associating. And it is quite easy and quite fast to be verified. You just take the Weierstrass polynomial of the curve. You take this strange polynomial here, on which we will return in a while, and you compute this matrix. So you have 3 points. You evaluate these 2 polynomials in all these 3 points. You construct this matrix here, and whenever the strong rank, which is a slight stronger version of the rank you use when you work over rings, when the strong rank is lower or equal than 1, then these 3 points associate. So it is really really amazing because this is a general way of proving that points associate by using rank information of matrices. And the second part is always beautiful, but it's more technical. It says that if you squeeze 2 columns, then you get a rank which is at most lower than the rank you are starting from. Okay, so now we see that this strange dotted polynomial comes into play. So the question is, what is this polynomial? I mean, where have you found this polynomial? The answer is that we found it by hard work, but we have called it shadow curve, shadow polynomial, and the curve defined by this polynomial is called shadow curve. And if you look at it, it's still an homogeneous cubic. So it's again an elliptic curve somehow with some changes of coordinate. But we have called it shadow because I mean, you may construct it directly if you know A and B, but it is not. I mean, it's not studied in the literature, and it is called shadow because it stays behind the main polynomial. I mean, nobody can see it if the main polynomial is in front of it, but also because there's this proposition here, which says that in absence of 3 torsion points, the elliptic curve and its shadow curve do not intersect apart from the infinity point. So this is really like a shadow, you know, they just touch in one point, the point at infinity. And if you see, let me remark that this is a beautiful strangeness in mathematics. So we started by assuming that the base field, for having this form of the Weierstrass equation, we assume the base field to have characteristic not 2 and 3. Then we leave out two torsion points for defining the operation, and now we leave out 3 torsion points for defining the properties of this curve. So the same properties you were requiring on the base field then turns out to be needed for the curve over these rings. So it's kind of interesting link. Moreover, maybe the most surprising behavior of these curves here is that you can play with the starting Weierstrass polynomial and this dotted shadow curve and together they give rise to another family of cubics, so another family of homogeneous cubics, which we call layers. So a layer is just the set of proper solutions of this equation here. Here, if you look at it, when you plug I equal to 0, you just find the elliptic curve, the proper elliptic curve over a ring definition. So the 0 layer is the elliptic curve we have seen in the first part of the talk, but then there are many other layers given by these equations, and all these layers are proved to be subloops of our elliptic loop, and also groups. So inside these layers, you have associativity. So this is a kind of a good result for us, because having no associativity at all would have been a mess. Instead, we have proved that you have associativity inside layers, but not only that, but layers are behaving particularly well. You have a stratification of the affine part of the elliptic loop made by the affine part of the layers. It means that when you do not have order 3 points in the underlying curve, then all the layers are distinct, they do not intersect in the affine point, and they cover entirely the elliptic loop. So the elliptic loop, the affine part of the elliptic loop is completely described in terms of layers. And what about the infinity part? Well, the infinity, the story changes. The layers all intersect in this small, very small group at infinity. And I'll try to provide you with a picture of what I'm saying. So this is more or less an elliptic loop, at least in my imagination. So you have here, you have in the affine part, you have all these layers, which are all distinct and disjoint. They all meet at infinity, but still there's a part which is not touched by any layer. So if you really want to describe the algebraic structure of the whole elliptic loop, we'll have to describe the structure of the layers and to find out what's there here. So what is the missing part of infinity? So let me start with the description of the structure of layers. We have this theorem, which generalizes the one we have seen for elliptic curves. We have, again, a short x-axis sequence. This zeta may be, it's an integer that may be explicitly computed. In the proof, we give the explicit characterization of this zeta. So we have, again, as before, a large kernel here, which has size p to the e minus 1. And then we have the projected curve. So again, if the curve is not anomalous, then we can use the splitting lemma and characterize the group structure of this layer here. So every layer of a non-anomalous curve is cyclic. So that's a good point for us. And then let me address the red question mark before. So what is the infinity part of an elliptic loop? Well, we do have this amazing theorem stating that the infinity is generated by these 2 points here somehow. So let me put under a quotation mark the generation, because it is not generated as a group, because the infinity part is not a group. It is a group if the exponent is lower or equal than 5. For exponents strictly greater than 6, we have proved that it is never a group. So neither the infinity part is a group, but it is always somehow generated by these 2 points here at the infinity, which is kind of nice. So it is generated, the sense of generation is that every point at infinity may be written as some multiple of this point here plus some other multiple of this point here. Again, I want to stress out the fact that, of course, if you add the associativity, then this would be a group generation. This group would be degenerated by these 2 elements, but you do not have associativity. So it means that if you have alpha 1, this point, beta 1, this point, and you sum with alpha 2, this point, beta 2, this point, you may not associate alpha and beta. And that's the reason why this is not a generation as a group. Okay, so this completes the characterization of the infinity part. So the infinity part is covered by these is generated by these 2 guys here. while the affine part is generated by loops, which are almost always cyclic for non-anomalous cases. Then we conclude this presentation with this theorem, which is insanely difficult to be proved. It requires a lot of both formal proofs and algebraic proofs. But yeah, I will save you the details. The final result is that you may play with all these layers together. And of course, you may do also other types of games. What we just tried to do in the final part of our thesis was characterizing the points lying over the same point and of a given order. And the order, we wanted it to be the same order of the base curve. So the question we are trying to answer with this theorem is, can you find the Q torsion point lying over a given point? So these are the points, I just said that loops are cyclic, but it means that they have a subgroup of order Q. So are we able to exhibit this group? And the amazing result is that maybe I will explain you with the picture. The amazing result is that for every point on the base curve you choose, you may find a very special line which is intersecting in every layer this Q torsion point. So the Q torsion point may be found by just intersecting this strange line, which we have called the Q line, with all the layers. So this is a way that they play together somehow. And if you think of it, in our mind, every layer corresponds to a proper lift of the starting elliptic curve, which means that this is a way of playing with all the lifts together. They usually live in different worlds. You may not sum points on different lifts. It makes no sense. There is no common operation. But in this world, we have just this framework we have defined. You may do it. So you may play with different lifts at once. So let me say that this result is this theorem is a very special theorem that works only when the exponent is true. For a higher exponent, this is not true anymore. So this is a very special theorem, which I mean, E equal true is the first non-trivial exponent, because E equal 1 gives you again the elliptic curves. E equal true is the first non-trivial, and from E equal 3 on, this theorem does not hold anymore. So I've concluded my short selected list of results. Now I want to say a couple of words about what's going to be next. Well, we have some results we were not able to prove, but we are we do strongly believe that they are true. So this is a conjecture on anomalous on the anomalous case. So this theorem here and the theorem the cyclicity theorem before hold only when the underlying curve is not anomalous. So what happens when the underlying curve is instead anomalous? So this is what we call an anomalous loop. Well, it seems, and it's surprisingly true, at least in the small exponent we have performed, that there is one integer m, and that integer prescribes the layers which has to be split. So all the layers are cyclic apart from 1 over p layers, the one indexed with multiples of with m plus multiples of p. So this is a very regular theorem that we strongly suspect to be true. We have proved something for small exponents, but we do not have a complete proof for the general case. And the second conjecture is linked to the maximality of these layers. So these layers are a very huge structure inside, huge associative structure inside loops. This conjecture says, okay, they are probably the largest possible associative structure. So we strongly believe that if there's a group which contains, if there's a group without order 3, and this is always assumed, if there's a group, a subgroup of the loop which is also a group, then it is either contained inside a layer or it is contained inside the infinity. So every affine associative structure is contained in a layer. This somehow reflects the idea that you may not find diagonal groups inside the layer certification. Again, we do not have a proof, and this is a more special part of the conjecture for the infinity part. Okay, what's next? What are the possible future research lines coming from this work? Well, first, I would like, and I will probably do in the future, study this strange curve we have defined. I mean, we have defined a large family of new cubics, starting from the shadow curves, and especially with layers. So the question is, how are them related to the starting elliptic curve? Still is something that we have not investigated so much, but it would be nice to understand them. Even especially because if they are, as we think, if they are linked to the lifts of the curve, then it gives an explicit way of characterizing every possible lift of the elliptic curve. The second part is specializing this result. I mean, our results are widely general. We do not have specialized the parameters for almost any theorem, apart from the last one, in which we require the exponent to be small. But of course, maybe stronger results may arise from specialization. Let's say take A equal to 0, for example. So 0 J invariant curves. Do they have more properties or do they don't? This is something that may be studied. Also, this is another interesting part. I would like to better understand the connection with these links, these lifts of the curve. And then, as a final remark, we have performed all this work over elliptic curves due to their special importance both in mathematics and in cryptography. But there are no reasons why one should not try to do the same, to construct other type of loops by enlarging these ideas over other curves. There are other families of curves that seem suitable. And when I say they seem suitable, I mean they have a good behavior at infinity. So for example, since in the audience there are a couple of people who has worked on polyperbola, I believe that polyperbola are one of this family of suitable curves over which such a lifting theory may be mounted. So I've finished my presentation. I think I'm in time. So now if you have questions.